so today we're gonna look at some related rates that involve some triangle stuff. So trig and like Pythagorean. So it says find the rate of change of the angle of elevation of the camera shown in the figure at 10 seconds after liftoff. The television camera at ground level is filming the liftoff of a rocket that is rising vertically according to the position equation S equals 50t squared, where S is measured in feet and t is measured in seconds. The camera is 2,000 feet from the launch pad. So what's our first step when we're dealing with related rates? Picture. Which they were nice enough to draw for us. Cool. Next step, equation, which also they were nice enough to give to us, yeah? So what's our equation here?
50t squared.
Be careful, because what are they asking us for the rate of change of? The angle of elevation. So I need to use the equation that has an angle in it, which is going to be our tangent. Alright. Then what can we do?
Take the derivative
Yep.
with respect to
Correct. So what is our derivative of tangent?
secant squared.
Secant squared. But because I'm taking with the derivative with respect to time, what do we have to multiply by?
D sub
Theta, right? That's what my, like, whatever it is. If it's tangent of happy face, now I have d happy face dt. So here I have d theta dt. Alright, and then on the right hand side, we just have an s. I hate it when they use s's, but you know.
Oh, it's S? I thought it was B.
What?
I can't see it.
No, it's an s. This is an s divided by 2,000. That's why I don't like s's, because they end up looking like 5s, or at least mine do. So I tend to, like, if I get to pick the variables, I don't make them s's. So what is the derivative of s? 1.
ds dt.
Yes, but then I also have 1 divided by
Oh.
2,000, right?
Yeah.
And then, yes, we have to have a ds dt. What are we solving for?
D theta dt.
So what do I need to do to get d theta dt by itself?
You need to put secant squared theta on the other side.
Okay, which I would do by
Dividing.
dividing by secant squared. But if I had 1 over secant squared, what is that the same thing as? Cosine squared. And you don't have to do that, but we are going to have to evaluate this eventually, so to plug that into our calculator is going to be a little bit easier if I have a cosine versus if we have a sine. Or versus if we have a secant. We're okay with that. So we technically have our formula now. Okay, so from here we need to plug and chug. What's our problem though? We don't have anything to plug right now. They don't give us a whole lot of information as far as numbers go. They do, however, give us a what?
Triangle.
Well, they give us a triangle. They also give us an additional formula. So notice that right now we don't have ds dt. Okay. However, they give us a formula for s, which means that I can take the derivative of that and plug in 10 seconds. Are we okay with that? So if I take the derivative of s, I get ds dt equals what?
100t.
But I'm taking the derivative with respect to t, so I don't have to multiply by anything this time. And then we're wanting to evaluate that at
10.
t equals 10. So what do we get? 1,000. Okay. So that's going to go in my ds dt. But what's the other variable that we also need to solve for?
Oh, yeah.
Mm-hmm. Is there a way that we could do that?
Use a triangle.
We could. Yeah. What do we want to do?
We know what S equals. Yeah, we know what S equals.
S equals what? So I need to know what s equals at 10.
Yeah.
So remember that this is ds dt. We also need to know s. So that would be 50 times 10 squared, which is 5,000. Yes?
Yeah.
So then we can use our tangent of theta formula.
Presumably.
Okay. So I have tangent of theta equals S, which is 5,000, divided by 2,000, which is also what? 5 halves. And then how do I solve for the theta, or get the tangent to go bye-bye?
10 -1.
So I have tangent inverse of 5 halves. Okay, we're going to go ahead and leave it like that, because we're going to have to plug all that into our calculator anyway, and so we don't want to give us an approximation too early. So we have d theta dt equals cosine of tangent inverse of 5 halves, and that is being squared. I just wrote it on the outside just so that y'all know that you have to evaluate the cosine stuff first and then square it. Okay? It's not the tangent part squared. Then I'm dividing by 2,000, 1, 2, 3, and multiplying by 1,000. And again, we're plugging all of that into our handy dandy calculator.
Yeah, no.
What?
My answer is not right.
No.
Did you get 0.06?
Yeah.
That's fine. So what? Give me 3 decimals.
Oh, the rate of change.
Oh, yeah.
Maybe.
0.06.
0, 6, 9. Okay, that's gonna be in what unit? Oh, what unit is your calculator in? Should probably be in radians,
Oh.
which is why you're getting a super small decimal there. What? Really?
Yeah. Oh my gosh, my calculator's almost dead.
Let's double check. Oh, where'd that?
Oh, yeah, it's the same even if you put rate.
Ah, why?
Because we're not using pi. Question mark.
No.
Supposed to be in radians or degrees?
It doesn't matter
Usually
in this case.
degrees.
That's what he was just saying. Most of the time,
Most of the time.
we want to be in radians, unless they specifically give you something that has a degree measure in it.
Okay,
And the reason being, right? Huh? Okay, notice here that I have tangent inverse, right? So this part right here is going to give me a degree, but then I'm taking cosine of that degree, which is going to give me a number, yes? Not an angle. So this number divided by that times that is still just going to be a number. And again, because that's the rate of change, not necessarily the angle itself. If I just typed in tangent inverse of 5 halves, that would be the actual angle at that time, but it's asking how much is the angle changing. And so that does just need to be a number. Which, notice, it's a rather small number. However, we're talking about 10 seconds, which is not very far after the launch. So it would make sense we are not very far off the ground, nor have we accelerated to go rather quickly yet. The farther that you get away from your launch pad, the bigger that number is going to get. Does that make sense?
So the answer is just 0.069, no
Yep.
unit.
Correct. Alright. It's a famous ladder problem. There's always a ladder on the unit, or on the AP test. They like ladders. Or one very similar to this, where it's something like a piece of cardboard is laying against a tree. against a wall, like a sign is laying against the building. Like, it's just something that is straight, laying against something else that is vertical. So, a bag is tied to the top of a 5-meter ladder, resting against a vertical wall. I don't want to know if it wasn't a vertical wall, like what type of wall it would be, but you know. Suppose the ladder begins sliding down the wall in such a way that the foot of the ladder is moving away from the wall. How fast is the bag descending at the instant the foot of the ladder is 4 meters from the wall and the foot is moving away at a rate of 2 meters per second?
No clue.
Lots of words, right? Which is why, what is it helpful for us
Draw
to
a
do?
picture.
Draw a pretty picture.
Step 1.
Yes. Okay, so we have a wall. Yes, it is a vertical wall. We have the ground. And then we have a ladder lying against that wall. Yes? Now, when we are dealing with things sliding or moving, usually it's kind of helpful to actually draw some directions to that, okay? So, on the left-hand side, what is happening? So I'll go ahead and draw my bag. Where's the bag at the top? Okay? What direction is my bag moving?
Down.
Down the wall, okay? And what direction is the foot of the ladder moving?
Right.
To the right. It's moving out. We're okay with that. And then do we have any givens?
The rate.
5 meter
Is what?
is the ladder length. It's 5 meters.
Okay, so that means that that's what in my
The
picture?
hypotenuse.
Correct. Because we have a what?
A right triangle.
Ooh, that's nice. That might come in handy. Okay. What else do we know?
The ladder. The foot of the ladder is 4 meters long.
Okay.
And the rate
It's
that
2
it's moving away is 2
Okay,
meters.
the rate of what?
The
Of
foot
the foot
moving
moving.
away.
Okay. So what might it be helpful to do?
Draw 2 meters per second.
I can't do that. But what I could do is I could label some stuff. So this is vertical. This is horizontal. Are we okay if I label this one Y and this one X?
Yeah.
Okay. Which then is helpful because now what is the 2 meters per second?
Oh, now it equals X.
Not X,
DA.
but
DX.
dx dt
Yeah.
is the 2 meters per second. And then that also helps us. What are we looking for?
DY DT.
Mhm. So by labeling those sides, it just gives us a little bit easier notation, okay? And we're specifically wanting that when the foot of the ladder, so that would be x equals 4. Yes? We're all okay with that.
Yeah.
Like I said, usually drawing your picture and breaking all the stuff down is going to be the hardest part. Once we can find the equation and take the derivative, most of these derivatives aren't super complicated. It's very basic, either just it's straight up just power rule, maybe a product rule from time to time, but usually that's it. We don't really run into a ton of like quotient rules or crazy other formulas. So, looking at this, what is something that relates, a formula that relates all of those things together? Okay, which is also called our Pythagorean theorem. In this case, what are acting as my 2 sides? Okay. What's acting as my hypotenuse? 5. Can I go ahead and put my 5 in?
Oh.
Why? Because it's constant. It's not changing. Okay? Now, can I plug my x equals 4 in? No, because that is changing. I cannot plug that in until when? After I've taken the derivative. So, speaking of derivatives, can I take the derivative of this?
Yeah.
Yeah, what's the derivative of 2x? Or sorry, x squared. 2x, yep. Well then what do we need to do though? Yeah, dx dt. What's our derivative of y squared?
2y dy.
And then what's our derivative of 5 squared? 0. Okay? And again, at the end of the day, what are we solving for? dy dt. So we need to be able to put something in for everything else. So, do I know what x is?
Yeah.
Yeah, what is it?
4.
Do I know what dx? That's a bad x. dt is 2. But now, what's the last thing that I need to know?
Why?
How can I figure out that y is?
Put it on
Pythagorean theorem.
the other side.
3.
I can use my Pythagorean theorem, right? So notice that I have x squared plus y squared equals 25, right? I'm specifically wanting this when x is 4. So we get that y equals 3. Are we all okay with that? And again, because I have taken my derivative now, I can plug stuff back in to find exact values. We don't want to start doing that until I've taken my derivative, though. But I have times 3 times dy dt. So 2 times 4 times 2, 2 times 3, dy dt. So what do we get? Which is also,
Negative 8 over 3.
so 8 thirds. Okay. What per what?
Feet per second.
Meters per second. Now, does it make sense that we are negative there?
No.
Yes.
Yeah, because my bag is moving down the wall. Yes?
Yeah.
So all that negative does is give us direction. Now, the more negative you get, actually the faster you get, the faster you're going down, right? But the only thing that the negative gives us is tells us which direction. Now, be careful though, okay? Because, so like, let's say it was like a different, like a part B, and I started to say, well, what if someone starts to push the ladder back,
Oh.
whatever, at a certain rate, okay? What would negative mean in terms of my foot of the ladder?
Towards the wall.
Towards the wall, right? So negative and positive is kind of just whatever you describe it to be, yes? But positive is going to be to the right. Negative would be to the left in the case of our horizontal movement, right? It's going to be up or down in the case of our vertical movement. Yes?
Yes.
Are we okay with that?
Yes.
All right. Continuing on.
This is the last one.
I think we have one more.
One.
So this says, find the rate of change of the distance between the origin and a moving point on the graph of y equals x squared plus 1 if dx dt equals 2 centimeters per second. So, what do we want to do first?
Find our derivative.
Well, no.
Picture.
Make a picture.
But we
We're
already
going to have a pretty picture. What's our second thing?
Find your derivative.
Well, no. What's the second step in our rate of change steps? Find a equation. But, yes, we also have that as well. So then, what can we do? Take the derivative of that?
Yeah.
We sure?
I mean, no. Well, yes. Take the derivative of that. Yes, with respect to time.
I'm confused. This is a question I would skip.
Real. Yeah.
Take
right?
the derivative.
Do you like?
So what does y represent?
That.
Yeah, it represents the graph.
This is
Does it?
It
The
represents
graph
the,
of that.
It
It's
represents.
gotta be the graph, right?
It represents the moving point.
Why do you feel like the math is
Maybe.
gaslighting me?
Does it
represent
represent
the
the moving point?
I don't know.
y equals height.
Okay, so yeah, y equals your vertical distance. Yes. However, that doesn't give us horizontal distance, right? Agreed? Are we okay with that?
Yes.
Okay.
Oh.
What would we use if I wanted to account for both horizontal and vertical distance?
The distance formula?
Yeah.
That's okay.
So, what is our distance formula?
E equals square root of Y1
X2
squared?
minus X1 squared plus Y2 minus Y1 squared.
But you know what's gonna be nice? What point are we using?
0, 0.
0, 0. That's nice.
Yeah.
So I just end up with x squared plus y squared there. Yes?
Yeah.
Also, what's nice?
Wait, we're using 0, 0 again?
Because it says the distance between the origin and the moving point.
Oh, okay.
This point gives me 0, 0.
And we were-
If they gave us 1, 1, then we would be plugging in a 1 and a 1 here.
Oh.
A lot of times it is going to be the origin, just because it ends up washing out a little bit nicer. But now we could go ahead and take the derivative like that as it is. But because in this case we have a secondary equation that's pretty straightforward to plug in, we can go ahead and plug that in. So what can we plug in?
X to the 4th plus 2x.
Huh? What do I want to plug in?
X squared.
X squared. Plus 1, right? For my y value. We're okay with that. Because they only give us dx dt, they don't give us anything about dy dt. So I could take the derivative of that, but eventually I'm going to have to do some plugging and chugging to figure out what dy dt is, or I can just put everything in terms of x's. So I get x squared plus, this is going to be x to the 4th plus 2x squared plus 1. Agreed?
Yeah.
There's your math right there. So I get x to the 4th plus 3x squared plus 1. We're almost there. Now what can I do? Take the derivative. Alright. So d prime, or dd dt. That's why I put d prime, because that just sounds funny. But that is your rate of change of your distance, d prime, equals, what are we going to have to do here?
Chain rule.
A chain rule. Okay. So it's going to come up front. A 1/2 times
X to the 4th.
x to the 4th plus 3x squared plus 1 to the negative 1/2 power times
4x to the 3rd plus 6x.
missing something.
Dx.
Times dx dt. Yeah, there we go. Because technically it's a double chain rule, right? It's just we don't actually see the doubleness part, right? But because I have an x there, my x is in terms of t's. I gotta multiply by dx dt. Now, what do we know that dx dt is? 2. So 2 times 1/2 is gonna give us what? 1. So I'm gonna move my 4x cubed plus 6x to the top. Again, remember all of this is multiplication. I just ran out of room. And then this is on bottom is going to be the square root of x to the 4th plus 3x squared plus 1. And that's my answer. They don't give us a specific x value that they want us to plug in. If they said when x is 1, then we would plug in 1 or plug in whatever x value it is. But because they don't and they just give us an original point and ask us for the rate of change, they're just asking us for the derivative of that, and that is our derivative of that.
Okay. Do we need to put a unit? Do we need to put a unit in anything, or is that?
No, like not when you're giving a formula. If they ask you like when x is 2 and you actually plug in a number, yes, then you want to put units on your final answer that way. Questions on that? So this one's actually these ones actually, as long as you remember to use the distance formula, that's the hardest part. Remembering to use the distance formula again, because most of the time they're going to give you the origin and they're going to give you an equation that's fairly easy to plug into. They're not as hard as they seem. Okay, so they're not ones that we have to skip. Okay. Alright, last one is the last kind of popular type.